Math 2414, volume shells. The shell method, example 2. All right, in the previous video, we kind of established a new technique called the shell method, but I'd like to kind of summarize it here. Let me put a partition line here. If we have a lamina that we're rotating around the y-axis, but we take a cut parallel to the y-axis, then we can calculate the volume if we can measure the radius, which is the distance from the axis of rotation to that cut, and the height, which is the height of that cut. And if we can represent those in terms of x, then the volume is the integral over the correct range of values of 2 pi times the radius times the height dx. And this would be a dx integral because the skinny side of that cut would be a delta x. However, if we had a lamina that we were rotating around the x-axis and we took a cut parallel to the x-axis, the radius would still be the distance from the axis of rotation to that cut, which in this case is a y value, and the height, quote unquote, would be the actual length of that cut in terms of the functions that define the lamina. And our volume would be the integral over the correct range of values of 2 pi times the radius times the height dy. Again, this one would be a dy integral because our cut represents a rectangle with a very skinny y dimension called delta y. All right, so let's find the volume of the solid formed by revolving the lamina bounded by y equals x and y equals x squared around the y-axis. Well, let's get the picture set up and then decide on a plan of attack. This is a perfect diagonal line. This is a standard parabola. Made the parabola kind of wide. The lamina bounded by those is right here in quadrant 1. And we are rotating this around the y-axis. And notice in the directions, I didn't say use the shell method or use the disc or washer method. The method that you use depends upon how you cut the lamina. Cut a little piece that you're going to revolve around the axis of rotation. If you cut parallel to the axis of rotation, use the shell method. Remember, parallel, shell. If you cut perpendicular to the axis of rotation, then use the disc or the washer method. If we cut perpendicular to the axis of rotation, we would cut this way and it would be a dy integral because the skinny side of that is a delta y. But if we cut it vertically parallel to the axis of rotation, then the skinny side of that is the x side, it would be a dx integral. So if your comfort zone is doing everything in terms of x, then you always cut this vertically to get that skinny dx side. Let's go ahead and do that, not because it's dx, but because we're practicing the shell method. And again, if you're going to use the shell method, you cut your lamina parallel to the axis of rotation so that when you revolve it, you get a shell. So let's figure out what we need to know. We need to know the radius and the height. Well, let's pick a generic point. Well, it's not a generic point. Let's pick the points on either side of that cut. One on the top boundary, one on the bottom boundary. This point would be x comma something, and the one on top would be x comma something. Now, technically, this would be x comma y. But on the parabola, what does y equal? X squared. So we can actually label this point as x squared. On this point, whose x-coordinate is x, it lies on the graph of y equals x. So here's a silly question. On this line, what does y equal? X. So we'd actually represent that order pair as x comma x. And remember, we're doing this all in terms of an x-coordinate, so that's why we're choosing that based on the way that we cut this. All right, let's see if we can measure the radius and the height. The radius is the distance from the axis of rotation to the cut. And right now that's just x. In other words, this is our radius. So we got one piece of the integrand. The height, however, what's that going to equal? Well, if you think about it in terms of y coordinates, it would be the difference in the y coordinates, the top y minus the bottom y. But up here, the top y is equal to x, and down here, the bottom y is equal to x squared. So there's the expression for the height. The only other thing that we're missing are the limits of integration. But the limits of integration can be found by equating these equations and solving for x. So for our limits of integration, we need to solve x is equal to x squared. Well, if we subtract x from both sides so that we can get the equation equal to 0, and then factor out an x to leave x times x minus 1, then we can put each factor equal to 0. X is equal to 0, and if I put x minus 1 equal to 0, that's going to solve to give x equals 1. So now I know my limits of integration. We're going to integrate from 0 to 1. Therefore, the volume will be the integral from 0 to 1 of 2 pi times the radius, which we didn't actually write it down anywhere, but the radius is equal to just the x coordinate. That's the distance from the axis to the cut. Times the height, which was basically the top function minus the bottom function, times x minus x squared dx. And then it becomes a calculus 1 problem. Let's evaluate this one the same way we did before, by pulling out the 2 pi and distributing the x to get x squared minus x cubed dx. You can almost put it on autopilot from here. The antiderivative of x squared is 1/3 x cubed. The antiderivative of x cubed is 1/4 x to the 4th. This is being evaluated from 0 to 1. 0 makes the antiderivative equal to 0, so we can ignore that. Let me rephrase that. The lower limit makes the antiderivative equal to 0, so we can ignore it. Otherwise, we couldn't. And if we substitute the upper limit, we get 1/3 times 1 cubed, which is just 1/3. 1/4 times 1 to the 4th, which is just 1/4. I'm not going to dilly-dally with the fraction arithmetic. 1/3 minus 1/4 is 1/12. If you don't know why, get out of my class. Just kind of kidding there, but seriously, I shouldn't have to explain how to subtract these. 2 pi times 1/12 is going to be 2 pi over 12, which reduces to pi over 6. So if you chose to do the shell method on this, by taking a cut parallel to the axis of rotation, and then coming up with expressions for the radius and the height, then we would just integrate 2 pi times the radius times the height, and we end up with pi over 6, if you chose to do the shell method. Now, I know this series of videos is about the shell method, but nowhere in the instructions did it say, use the shell method. It simply said, find the volume. What if we had chosen to use the washer method? So here comes a second version of the answer to show you that there's more than one way to do many problems. Let's get the lamina set up again. Okay, so here's y equals x on top, y equals x squared on the bottom. And by the way, the only time the parabola is below the line is between 0 and 1. And we're still going around the y-axis. If you had decided, no thank you, I'll just do the disc or washer method, then you have to start by taking a cut that is perpendicular to the axis of rotation. And since that's the y-axis, our cut would have to go sideways. I know what I need to do. Well, first off, this is going to be a dy integral because the skinny side of that rectangle, that cut, is a delta y. I know what I need to do. I need to integrate from a to b, whatever those are going to be in this case. Actually, it's going to be 0 and 1 again because this line is y equal x, and here x is equal to 1, and since y equals x, that means y is equal to 1. So our limits of integration are going to be the same. But this will be a washer, because when I take this little stick and rotate it around, I get a washer with a hole in the middle, also because the axis of rotation is not a boundary on the lamina. But the volume is going to be pi big R squared minus pi little r squared dy. Remember that capital R is the outer radius, which is the distance from the axis of rotation to the furthest boundary on the lamina. And little r is the inner radius, which is the distance from the axis rotation to the nearer boundary of the lamina. But we need to represent these in terms of x's and y's. Well, if we look at this point on the left boundary, that represents r, and we think about this as an ordered pair, x comma y, but on this line y is equal to x, then the radius is just the x coordinate. So we know that little r is equal to x. And on the on the right side of the boundary, we have yes, the radius is equal to x, but do you know why I don't want to use x for the radius? This is a dy integral. So let's go back to this ordered pair for a second. We are cutting this horizontally, which means we are choosing some y value at which to cut. So when I label these ordered pairs, I should really start with where I cut the y value. And on this line, what does x equal? X equals y. So that ordered pair could be written y comma y, in which case the radius is y. What about this ordered pair? On the graph of y equals x squared. Well, we cut at y, so we'll start with the y coordinate there. But on this parabola, what does x equal? Well, this equation doesn't say x equal, it says y equals x squared, even though it's kind of sloppy right now. But I need to know what the x coordinate is in terms of y. I would have to solve this and get x equals the square root of y. Technically, x equals plus or minus the square root of y, but since we're on the right side of the y-axis, the x's are positive. So on this point, whose y-coordinate is y, the x-coordinate would have to be the square root of y. Which means the outer radius is the x-coordinate on this parabola, but on this parabola, the x-coordinate is equal to the square root of y. So we got everything we need. We've got the limits of integration. Pi times the outer radius squared, but the outer radius is the square root of y. Minus pi times the inner radius squared, but the inner radius was just y. dy. So this will be the integral from 0 to 1 of pi y minus pi y squared dy. I think I'll factor out the pi and integrate at the same time. The integral of y is 1/2 y squared, or rather the antiderivative of y. The antiderivative of y squared is 1/3 y cubed. This is going from 0 to 1. The lower limit annihilates the antiderivative, so we can ignore it. That's only good for lower limits when they make the antiderivative 0. For the upper limit, if we plug in 1, we're just going to get 1/2 minus 1/3. 1/2 minus 1/3 is 1/6, so the volume is pi over 6, which it should be because that's what it was with the shell method. So the reason I did this one twice was to point out that there's more than one way to do some of these problems. But which way is better depends. In some cases like this one, both ways work. But in other cases like the previous example, one way would work but not the other. Your choices are dictated based on whether you want to take a cut perpendicular to the axis of rotation or a cut parallel to the axis of rotation. I think I got another example where it's not always obvious which one to do. We do. It'll be the fifth and final video, I should say, the fourth and final example.